All right, guys, in this little video, what we're going to talk about is this idea of sharing a little bit more. And now that we're able to do Lewis structures and we're able to talk about the different bonds and all that sharing that happens, let's talk about how well things are shared, okay? So now, I know growing up, I had to share, okay? My mom constantly was telling me, hey, share with your brother, share with your brother, share with your brother. I really wanted to share with my brother, but I always kind of had to, okay? Now, in the world of sharing, sharing doesn't always have to be equal, okay? When I was a sophomore in high school, I got my driver's license, and I was sharing a car with my older brother, who was a senior. So I'll guarantee you that sharing was not very equal because he was a senior and I was a sophomore. So the result was I only got the car when he didn't want it, all right? But we still shared a car. Now, that kind of idea still portrays when we talk about bonds and talk about the sharing between things. We've already learned before that different elements have different amounts of electronegativity, or this ability or this desire to gain electrons in a shared bond, okay? Well, when you have two different elements come together that have different electronegativities, you have unequal sharing. So that's what we're going to be talking about here. Now, to do that, we need to talk about bond polarity. So first of all, let's talk about what polarity is. Polarity is basically having electronic poles to it. Very much like our planet has magnetic poles. We have the North Pole and the South Pole. We have sides to it, okay? The polarity, or those poles, come from an unequal amount of sharing. Now, this is not a light switch. This is not an on-off kind of thing. It's a continuum of unequal sharing. You have perfectly equal sharing, like we see here between two chlorine atoms, okay? When we have perfectly equal sharing, we call that a non-polar, meaning not sided or no poles to it, covalent bond, all right? As we get difference in electronegativity that gets greater and greater and greater, okay, we have breakpoints, okay? So at 0.4 of a difference, okay, so if it's greater than or equal to 0.4 of a difference in electronegativities, we would then call that a polar bond. If we have a difference of equal to or greater than 2.0, we now say that the polarity difference between those two different things, or the electronegativity difference, I should say, between those two different things is so great that we actually no longer are sharing at all, but we now start to consider that ionic, okay? So what we can do is we actually should be able to take a look at our periodic table and look this stuff up. So if you go to the back side of our periodic table, and I'm going to pull that up here for you guys here, that periodic table I shared with you guys previously or got it in class, there is an electronegativity table on the back of that, okay? So let's take a look at hydrogen, which is right here. And hydrogen has an electronegativity of 2.20, okay? And let's take a look at chlorine, which has electronegativity of 3.16, okay? So in that bond between hydrogen and chlorine, there is sharing, okay? But this bond that is being shared is not shared equally. Chlorine is more electronegative right here. So more of the time, the electrons spend on the chlorine side and less on the hydrogen side, okay? So if you want to take a look at that visually, if you imagine hydrogen and chlorine together and they're sharing electrons, the chlorine kind of keeps them more often. So you kind of see I'm kind of drawing it by density here. The electrons stay over here more often. Sure, they get it, sometimes they go over by hydrogen. But all in all, if we were to map out electron density, we would see that the density around the chlorine compared to the hydrogen would be much, much more dense, okay? So we know that the electron spends more time on the chlorine side than the other. Now, the difference here, if we do a little bit of math, 3.16 minus 2.20, what is that, 9.4, 0.94? So we see a difference in 0.94. Well, that is greater than 0.40, not 00, 0.40. So we call this a polar covalent bond, okay? If we get a scenario where we are, the electronegativity is so great, so let's take, for example, sodium combining with, let's just do fluorine, okay? So fluorine, sodium fluoride, where sodium's electronegativity is 0.93, really, really low, and fluorine's is 4. So now we have a difference, is that 3.07? That's a huge difference in electronegativity. So really, there is no sharing here at all because the electrons between fluorine and sodium, they just spend their entire time on the fluorine. Okay, so that valence electron, that bond, is always to fluorine. Always, 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 always. It never really goes over there. It's always on the fluorine. Okay, so what holds that together? Well, sodium ends up being positively charged because of that, and fluorine negatively charged. So it's that charge imbalance that creates the attraction in this bond. And we don't call that a polar bond at all. We call that an ionic bond. Okay, so this difference in polarity, if we go back to our slideshow now, can be tracked. As long as they're between 0.4 and 2, we call that a polar covalent bond. It's an unequal sharing, but they're still being shared. Once we break 2 in that differences in the electronegativity, now the difference is so great that we don't even call that sharing anymore. Now we have an ionic bond. So really, an ionic bond is just an extreme case of polarity. It's so polar that it really isn't even shared at all anymore. Okay? That's important to us because as we start to look at the chemistry in the future units of how things act chemically, things that ionically bond will act chemically different than things that are polar versus chemically different than things that are nonpolar, okay, in terms of what they are. Now, being able to solve for polarity of a bond is pretty easy, okay? You just subtract two numbers, right? You always take the big number, subtract away the small number, that's your difference, okay? And the element that has the higher electronegativity is always the one that's going to get the electrons more often, okay? So in this example, chlorine has a higher electronegativity than hydrogen, so it's going to be the one that has the electrons more often. Here it's so drastic that chlorine keeps it 100%. Notice this little symbolism here, we'll talk more about that later. This represents how the bond looks. So it's kind of like a plus sign with an arrow pointing to it. So what they're trying to represent here is that this side becomes kind of positive and the bond pulls the electrons towards the negative side, okay? So we often see this symbolism to help represent polar bonds and which direction the electrons are being pulled towards, or the arrow points towards the more electronegative substance, all right?